Hello, hello, everyone. Welcome back to this last session of a very successful conference. I'm honored to be the session chair and also to introduce our last keynote speaker, Professor Bryan from Yale University. A few years before COVID, I went into Bryan at a conference and I said, "Oh, you have been doing so well, making such a great impact." And he stared at me. I wonder, what do you think I'm most famous for? And then I went blank, because he's done so many things, right? So I just, options and volatility. And I forgot to mention all his recent work in machine learning and textual analysis and so on and so forth. So today, I'm just going to introduce Bryan Kelly as the future Nobel Prize winner. And Bryan, you have 15 minutes, and following Bryan's keynote speech, we will have about 10 minutes question and answer. So without further ado, I will turn over the podium to Professor Bryan Kelly.
Great, thank you so much. Can everyone hear me okay? So, first of all, I want to thank the organizers for putting the program. It's an honor to participate. I wish I could be there in person. The topic that I'm going to cover today is based on a collection of papers that I've been working on the general theme of virtue of complexity. And we'll talk about exactly what that means as we go through. But this is based on a collection of papers. All of them are with Semyon Malamud. And there's also student collaborators of mine, Kangying Zhou and Barry Ke from Yale, and Antoine Diedesheim, who was a student at EPFL of Semyon's and is now a professor in Australia. So let me start with some background. So I'm getting old at this point, and I can think about the tradition in econometrics in which I was raised. So I was raised in a tradition in time series econometrics. And in time series econometrics, there's a very famous book that we often use. It's Box and Jenkins textbook. If you open up that textbook, you see in the first chapter, there are basic rules of model building. And the first rule in the first chapter of that book is that it's important in practice that we employ the smallest possible number of parameters for adequate representations, right? So this is, they refer to the principle of parsimony. This goes back to an idea from a very famous statistician, Tukey. So the reason why I want to start here is that while we as financial econometricians are often taught about this idea of building parsimonious models with the view that those are going to be the most beneficial out of sample, they'll be the most robust out of sample. It indeed clashes with the large parameterizations of modern machine learning. So we don't have to look very far to see this. So if you look at, for example, the GPT model that underlies ChatGPT, that's a model with billions and billions of parameters. The most recent version of it, in fact, has 1 trillion parameters. Right? The types of neural network models that Da-Cheng Xu and I have worked on, right? These are massive models by finance or economic standards, 30,000 or more parameters, but they're small models by machine learning standards, right? But they seem like they'd be too large for most finance applications, but they seem to work very well empirically. So if you think about this from the perspective of the people that trained me in time series econometrics, you'd say, wow, this is really just too many parameters. There's no way this could work out of sample. There's going to be too much overfit, and it's not going to be able to do anything realistic when we go out of sample. But of course, this is incorrect, right? And we know this from machine learning. So one of my favorite papers is this Belkin paper, where he lays out very clearly that in machine learning, you can look across disciplines and you see that very typically the best models at any point in time are the very largest models that have been proposed to date. So if you look at a model with billions or trillions of parameters in it, you're exactly fitting the training data at that point. But even if you exactly fit the training data, you don't seem to be overfit in the sense that the model is still giving the best out of sample performance among all the models that have been considered. So we need to think about what this is telling us. What is the logic behind this? How can this actually happen? But at the very least, it seems like modern machine learning has turned this idea of the principle of parsimony on its head. Now, the point of this talk is to say, well, people have been thinking about this in statistics and machine learning. The point of this talk is to discuss how it's happening in finance too. So I alluded to some of my work with Da Cheng. There's been a number of papers not just by me, but also by others in the area that show very reliable gains from using machine learning methods in portfolio prediction problems, in portfolio choice problems, and factor modeling. And consistently, we see there are large empirical gains over more standard, simpler models, right? But there's little understanding of why up till now. And I think that has led to a significant skepticism that we're doing anything more than just overfitting the data. So what I want to do in this paper, you can think of it as trying to build the case for why we should be doing financial machine learning. Think of it as a response to the skepticism about the viability of machine learning for finance. This is going to be a theory paper, right? It's a statistical theory paper. And the main theoretical result is that portfolio performance derived from a machine learning prediction model is going to be increasing in the complexity of that model. Now, when I talk about complexity, what I'm going to be talking about specifically are the number of parameters, or the number of parameters relative to the number of training observations that you have. So think of that as a ratio. P is the number of parameters, T is the number of observations. As P over T gets large, bigger than 1 for sure, maybe much larger than 1. You have many, many more parameters than you have observations. You'll see that you'll improve portfolio performance by pushing that P ever larger. So it comes across as a counterintuitive result, but I'll try to spend as much time as I can going through the intuition for what drives this result. The nice thing about the result is that it is a clear answer to the skeptics, because it tells you that the prior evidence of empirical gains that we've seen in the literature are in fact what we should expect by deploying machine learning for these types of problems. And then at the end of the talk, we'll go through some of the empirical support for this theory. I want to emphasize that, as I said, right, this is based on a collection of papers. I'm going to take you through the theory in the first paper, which is sort of the simplest analysis. It's a pure time series setting. And in that setting, the theory is sort of most tractable for us to talk through. But I want to emphasize that we have additional papers that deal with the panel prediction problem, which is really about the cross-section of returns and thinking about asset pricing models in particular, right? How do I build asset pricing models for many assets using complex specifications? And then we also have a version that says, let's look at this idea of the virtue of complexity much more broadly, empirically. I'll have one case study in this paper, but in a follow-on paper called The Virtue of Complexity Everywhere, we've looked at empirical analyses across all asset classes, and you see the virtue of complexity as a very, very robust and prominent, pervasive phenomenon. All right, so here's the way that I'm going to introduce the problem. I'm going to think of it sort of as, imagine that you're running a research team, and you have an analyst that's on your team, and you say to the analyst, listen, I want you to analyze some return prediction. Let's imagine that we're trying to forecast the market return. Now, I'm running the research team, so I'm going to pick the predictor variables. I'm going to say the predictor variables are in a vector G here. So that's just it can come from my prior on what is a good set of predictors, or it could be we've agreed already collectively on what a good set of predictors is. But think of G as a fixed set of predictors. I hand those predictors to the analyst and I say, go and build the best return prediction model that you can build. Now, analysts these days, unlike me, are trained to know that they're not really well equipped to do model specification. They can't pick the correct model themselves. So what they're going to do is they're going to use some machine learning. They're going to use a generic approximating model. For example, a neural network. They're going to say, I don't know what the function f is. So instead, what I'll do is I'll turn to any of a number of good approximating functions that have been used in other applications. Those approximating functions always take the same form. It's a type of non-parametric regression. So what I'll do is I'll take those G's and I'll build nonlinear basis functions from them. So those nonlinear basis functions, if I'm looking at a neural network, take a form like this S down here. So any neural network can be thought of as taking a linear sum of the predictor variables and then feeding them through some nonlinear activation function. All right. So I can produce many such nonlinear basis functions of these G's. It's like starting with a set of raw inputs, the G variables here, and building it out into a relatively large number of intermediate nodes. Then once I've built it out, I've basically given myself an opportunity to move back to a very sort of standard regression setup. I've taken my original data, I've expanded it out nonlinearly, but the final step in a neural network, the final step in one of these approximation models is simply going to be to run a regression, right? Run a regression now of my target variable, the market return, on all of these nonlinear basis functions that I've built. Okay. So that would be the way that typical analysts these days would approach this prediction problem. But the problem's not done because a key input to the analysis is going to be how many of these intermediate basis functions should I build? And that's not going to be an easy question for my analyst to answer. And really, before working on this paper, I don't think I had myself a good idea for what that answer should be. So we want to provide an answer. That's sort of a way to view the entire formulation of this paper. So to summarize, here's the way we're thinking about the problem. You have some true empirical predictive relationship between the predictors G and the outcome variable R. You say, I don't know how to specify F, right? I'm not omniscient. I'm just a person that doesn't know exactly how predictive relationships work in complex systems like markets. So instead, what I'm going to do is I'm going to use a generic approximator like a neural network. And that's going to be represented in some sort of nonlinear regression like this. Now, the constraint is that I have a limited amount of data to train on. I have a fixed amount of data, T, right? Based on that, I need to make a decision about how big of an approximating model to use. How many of these terms, what should P be when I go to run this approximating model? There's, of course, a trade-off. Now, in the traditional econometric view, that Tukey, that Box and Jenkins, the parsimonious view, right? The view is that we should use a simple model. We should use P much smaller than T. The rationale being that this model has low variance because it's parsimonious. I have enough observations to build efficient low variance estimates of each of the parameters. And that's going to give me low variance forecasts when I go out of sample. And that's an attractive feature. But of course, there's a cost to using such a simple model. The cost is that it's not going to be a very good approximator. If I only have a small number of terms in this approximating function, it's going to be a coarse approximation. Now, I could go the other way. I could use an extremely large number of parameters. I could even take P larger than the number of observations that I have, as long as I allow myself to do some shrinkage, for example. What do I get by doing this? Well, by making P larger, I get a better and better potential approximating model, right? I give the model the ability to fit the data more accurately. But it may behave poorly because I'm going to have very few observations in essence to inform each of those parameters, right? And it certainly will require some shrinkage. So the central research question is this: which P should my analyst use? Does the benefit of more parameters justify the cost, the variance cost, if you will, of estimating those parameters? And the answer is a pretty surprising and a pretty stark answer, which is you should always use the very largest P that you can compute. The bigger the model, the better its expected out-of-sample performance. So that's the key result from this paper. And we're going to talk about what that means. We're going to be talking about performance both in terms of forecast accuracy, so things like R-squared or MSE. But for my purposes, what I'm most interested is what does complexity mean for portfolio performance? Once I build this model and I go and use it to construct an optimal portfolio, does the portfolio behave better when I make P larger? And the answer is absolutely. The Sharpe ratio of a portfolio based on a large prediction model is going to be ever increasing in the number of parameters. It'll start to eventually flatten out, but it's going to be increasing, never decreasing in the number of parameters. Okay. So just to summarize then, the statistical environment, we have a time series regression. R is the market return. We have a large number of predictor variables, S. You should think about this S as being a set of generated predictors, right? They're generated from some underlying smaller predictor set, a fixed set of predictors, those Gs. So that means that this linearity in the specification is without loss of generality, because the nonlinearity shows up within the S functions. Now, the S functions I'm going to take as given, and I'm just going to be focusing on what happens as I estimate the beta. So beta is a p-dimensional vector. I have one for each of my basis functions. And as I make my approximating model bigger and bigger, I have to estimate more and more betas. All right. One assumption that we're going to have here is that the predictability is sort of in expectation equally spread across the predictors. This is very standard in thinking about neural networks, right? The idea is that when I build a neural network, I don't know ahead of time which of these nodes is going to be the best reflection of the predictive information. When I build a neural network, what I do is I take my information in my original Gs and I sort of spread it out in some even way across the intermediate nodes. Now, that's an ex ante perspective on how I use information. Ex post, of course, some of these nodes are going to be better predictors than others. That's always going to be the case. But from an ex ante perspective, I can't know as the model specifier which of these particular nodes will be better. If I knew which one would be better, then I could impose a prior that forced the model to focus more on, say, this first node if I thought that was where the predictability would be concentrated. So this assumption here is just saying that this is a very standard neural network setup. I can't tell you ahead of time which of the intermediate nodes of the network are going to be the ones that sort of capture the most useful form of the predictability. Other small assumption is that the total predictability in the system is going to need to be fixed. That's just to make sure that Sharpe ratios don't diverge to infinity. All right, so that's the statistical portion of the problem. I also need a finance portion of the problem, and that's going to show up in the form of a trading strategy. In order to analyze how complexity, how model size associates with portfolio performance, I need a translation between the prediction problem and the trading problem. And we're going to use a very simple formulation here. It's an approximately optimal trading rule. But what we're going to do is we're just going to take a linear trading rule where we build our forecasts period by period. And we say, when we're forecasting a high expected return, we're going to take a larger weight, a larger timing position in the market. And when we forecast a lower expected return, we'll take a lower timing weight. So it's really a timing strategy. That's the nature of this problem. It's a univariate time series prediction problem. So any trading strategy is going to be a timing strategy. And we're just going to linearly scale our positions in the market up and down over time as we vary our expected return forecasts from the machine learning model. All right. None of these results that I'm going to show you are actually very sensitive to the details of these types of specifications, but perhaps in the Q&A, if there are any questions, we can discuss some of those ideas. All right, so what do I want to accomplish here? First, the goals of the theoretical analysis. We're doing machine learning here, and we're doing high dimensional modeling, right? Which means that we don't have much interesting to say about in-sample. In-sample, you are just training, and you're burning all of the information that you have at your disposal. It's very likely that in sample, when you use a large model, you're going to effectively exactly fit your training data. So you have nothing interesting to say about the model in terms of its performance and training data. And this is, of course, the big distinction between machine learning and traditional econometrics, where we're doing inference in the form of hypothesis tests and so forth. Hypothesis tests are about performance of a model in sample. And you can do that when you have asymptotics that apply in sample, things like settings where T is much larger than P. In that type of environment, you can say things about what happens in sample, and you have interesting objects you can learn from the data in an in-sample sense. In machine learning, when P is very large, you can't say anything reliable about what happens in sample. Everything that we care about is the expected behavior out of sample. So what I want to do with the theory, and every result that I'm showing you here, even if I don't say it explicitly, is an expected out of sample object. The point is that I want to be able to characterize this stuff mathematically in terms of my expected out of sample behavior. Now, to do this, I need a different type of limit theory. I can't use traditional large T asymptotics to do this. The reason being, of course, is that P, I also need to think of as being large. And so in order to accomplish this, I'm going to be using a limit theory from random matrix theory, which allows us to take limits as P also goes to infinity. That means we're going to have objects in our statistical analysis, things like covariance matrices of predictors, whose dimension is increasing, right? I'm taking the limit as the size of a covariance matrix grows to be infinite dimensional. That's very different than traditional asymptotics. Traditional asymptotics, we hold the size of that covariance matrix fixed, and we send T to infinity. And that allows us to recover the true covariance matrix. That allows us to do things like hypothesis testing with central limit theory and so forth. That's not what we're doing in this paper. What we're doing in this paper is random matrix theory, which means that we're going to be characterizing models as the models themselves become extremely heavily parameterized. P goes to infinity. All right. So I'm not going to spend a lot of time on the details of the mathematical underpinnings here. I'm going to show you what the results imply, what the theoretical results imply via a calibration, so we don't have to get bogged down in the math so much. Before explaining the intuition for the virtue of complexity of results, I think it's useful to just do a quick recap of background from least squares, because it gives us a little bit of a context to be thinking about where complex phenomena come from. All right, so a very useful way to think about the least squares problem in our setting is to think about it in the form of a system of equations, right? One way to formulate the solution to a least squares problem is to think of it as a system of equations that we're solving. Each observation that we have in the data is one equation. All right, we have T equations, one for each observation. And then we have a set of parameters. In OLS, right, if we think of P being less than T, the fact that we have more equations than unknowns means that there's a unique solution for beta. And it also means that the beta is not an exact solution to the equations. There are errors, right? So this is the case where we don't exactly fit the training data. When P is less than T, we generally don't fit the training data perfectly, right? There's some residual, and there's a unique solution for beta. When we go into machine learning, we're stepping away from this traditional setting where there's a unique solution and there's some residuals. All right. When we go into machine learning, we need to recognize that, well, suppose that I have a model that's already big in some sense, that P is exactly equal to T. What's the solution to the system of equations in that setting? Well, when P equals T, of course, I can find a solution, and that solution exactly fits the training data. The solution in that case is unique. It's the first unique solution that exactly fits the training data. That happens when I get to a parameterization that's large enough that I have one parameter for each observation in my model, in my data set. But I can go past that, right? I can start to ask questions like, what if I add more parameters that I have observations? Well, now, if you think about that system of equations, if you have more unknowns than you have equations, well, now you have an infinite number of solutions for beta. And this is a problem. All of those solutions exactly fit the training data, but there's an infinite number of them. So what do we do in that setting? Well, typically what we do is we augment the problem so that it gives us a unique solution. And that's essentially what ridge regression does. When I introduce a ridge penalty, it means that I take this poorly defined inverse. When P is greater than T, this inverse covariance matrix of the predictors is ill-defined. And so I make it well-defined. The way I make it well-defined is I add a little bit of an identity matrix. Z is my ridge penalty. I is the identity matrix. If I add a little bit of identity to this covariance matrix, all of a sudden I'm back to a unique solution, and this inverse is well-defined. Right. It's interesting then to recognize that you actually can come up with a solution that exactly fits the training data and is unique, even if P is greater than T. How do you do that? Well, you just take an infinitesimal amount of shrinkage. You can think about this as the limit as Z goes to 0. Right? At 0, there's an infinite number of solutions, but in the limit as Z goes to 0, I can find an ever smaller Z that gives me a unique solution, and that unique solution is going to exactly fit the training data. That's has a name in statistics. It's called ridgeless regression. And ridgeless regression is kind of fascinating because it has this great interpretation. It is the solution to the system of equations when P is greater than T that exactly fits the training data, but it's unique in that among all of the solutions that fit the training data, it's the one with the smallest variance, the smallest L2 norm. Right? And that makes sense because when we're doing ridge regression, we're putting an L2 penalty on our coefficients. So adding an infinitesimal, a very tiny amount of shrinkage gives us a beta that has a relatively small norm. It's still enough beta to exactly fit the training data, but it doesn't use any excessive L2 norm, right? It's the smallest one that accomplishes that exact fit. All right. So with that basis in mind, we can go now to thinking about the virtue of complexity and how it works. So I'm going to begin in the bottom of the slide here. So I'm going to be describing an object C. C is going to be the ratio of parameters to the number of observations. So when C is large, we're in a very complex setting. When C is small, we're in a traditional setting, right? When C is close to 0, we actually have our standard asymptotics. So what happens when C is small? Well, when C is small, our betas get very precisely estimated. It means that all else equal, we have a small L2 norm of those betas. And interestingly, we can see already that as I start to increase the parameterization, the L2 norm of that beta begins to grow. Some of that is good because some of that increase in L2 norm means that the model is picking up a little bit of predictive information. It's finding meaningful predictability, so it makes the betas a little bit bigger. But very quickly, that L2 norm becomes excessive. As I start to push P close to T, that is when I hit C equals 1, my L2 norm explodes. And that's because I'm exactly fitting the training data, right? In more traditional thinking, we would call this overfit. All right. You see this in R squared as being essentially the flip of the beta norm plot. As the beta norm explodes, we get very high variance forecasts, and that translates into big negative out of sample R squareds. Now, here's the surprising part about complexity, is that when I start to push the parameters even larger, so that I have C greater than 1, something counterintuitive happens. The L2 norm starts to shrink, right? The variance of the betas, the magnitude of the betas starts to come down. Even though I'm adding more and more terms, the L2 norm is shrinking. Why is this happening? Well, it comes back to this logic of systems of equations and how we solve those systems of equations when we do least squares. So think about it as I increase the complexity of a model, right? Once C is above 1, I'm always able to find an infinite number of solutions that fit the data. When I do ridgeless regression, all right, and that's shown in this top blue line here, the one that has the most variable behavior in beta. So let's focus on that. When I'm doing ridgeless regression, if I have C equals to 2, I'm finding a solution that exactly fits the training data that has the smallest L2 norm. Why would it be that if I make my model even larger, if I push C to 3, for example, that the L2 norm gets smaller? Well, think of it as you add more parameters to the model, you've actually increased the space of solutions for your L2 problem, which means if you've increased the space of solutions, you can find an ever smaller L2 norm solution that'll fit. You've given yourself more possibilities to search across. You can always find at least a smaller solution. And that's true as you continue to expand parameterization. Okay, so this is the surprising feature of complexity. When you add more complexity, the fact that you're picking a solution, that solution will exactly fit the training data, but it's going to be tilted towards having a small L2 norm by virtue of the fact that we're trying to find a unique solution in a sensible way, a unique solution with a small magnitude. In doing that, we see some interesting things happen. First of all, we start to see the R squared recover, right? The beta norm comes down, the R squared starts to recover. In fact, if we go out far enough, this R squared will start to become positive. I've also drawn on this slide, not just the ridgeless case, this is the smallest amount of shrinkage we could use, but also when we add additional non-trivial shrinkage. And you see the role of additional non-trivial shrinkage is, of course, to control the magnitude of this beta more actively, right? Even to the case where we could have places where, you know, the R squared is increasing throughout the complexity range. Okay, so this is an active topic in statistics literature. It falls under the heading of benign overfit or double descent. You'll hear those phrases a lot. But the point is, the surprising feature here is that as we increase model complexity, right, we have improving performance of these models in a predictive sense. What I want to focus on in this paper is what complexity does for performance of trading strategies built on these models. And so the first thing I want to point out is that as I vary complexity, it's the case that the beta norm that we were looking at on the previous slide translates 1-for-1 into the volatility of a trading strategy. As I make my betas bigger and bigger, I increase my forecast errors, and that makes my volatility in my trading strategy bigger and bigger. So whenever I'm in a situation that the beta norm is large, my trading strategy is going to be highly volatile. So really, in order to understand complexity and how it affects asset markets and trading, it's really natural to be thinking about the main effect is coming from volatility. Again, the surprising feature here is that, and I think this is the thing that a lot of finance practitioners find most surprising, is that when I start to push my parameters beyond the number of observations I have, I actually end up with a lower trading strategy volatility than if I were somewhere in the range close to the number of observations. Now, this bottom plot shows the expected return of the trading strategy. Now, this one I think is a less surprising result. What it shows you is that the expected return of a trading strategy is strictly increasing in complexity. That is very intuitive because the expected return is not about the magnitude of my forecasts. It's about how good are those forecasts on average. And what is the key point of adding complexity to a model is that I'm deliberately trying to build a better and better approximator. Of course, as I better and better approximate the true predictive association, a trading strategy built off of that predictive association is going to perform better. So the key point here is I increase complexity, expected returns naturally improve. That's the benefit of better approximation. The surprising thing is that we would have thought that the variance cost of complexity was higher. It's only high in this intermediate range. When you go to very complex models, the complexity cost drops substantially. So to move to Sharpe ratio, I need to think about the ratio of these two, and that's shown here. And this is what we think of as the main theoretical result of this paper, is that as I increase complexity, the Sharpe ratio of a trading strategy in the complex region is strictly increasing in the number of parameters. Eventually, this plot will flatten out, right? But the main point is that going from a small model to a large model, holding the set of underlying predictors fixed, is going to translate into a strictly higher Sharpe ratio under fairly general conditions. All right. So this is the rationale for this phrasing, the virtue of complexity. The complexity is a virtue. As I add more parameters to my model, the approximation benefits dominate the variance costs of that heavy parameterization. The reason is because There's a lot of implicit shrinkage that happens in complex models due to the fact that I expand the space of solutions and I'm always picking small solutions. Recognize that when I'm in the ridgeless case, all of these models are exactly fitting the training data. Anytime C is greater than or equal to 1, I'm exactly fitting the training data. But that does not mean I'm overfit. I'm only overfit if I'm using more parameters than I actually need. But if I have to approximate a function that's unknown, I actually need all of those parameters. It's like saying that the only way I get to a correctly specified model is if I push the number of parameters to infinity. It's only when I have an infinite set of basis functions that I recover the true predictive relationship. So the way you should think of overfit in the traditional sense is that overfit is a fact that you have too few observations. It's not that you have too many parameters, right? Okay, so this is a different perspective. Even when you exactly fit the training data, you're underfit because you're exactly fitting the training data just because you used up all your observations, not because you had too many parameters, right? And that's exactly this rationale for why increasing complexity can continually produce better and better performance, because here you're always exactly fitting the training data as you increase C, but you're doing it in a more appropriate way, in a more accurate approximating way. Okay, so that's the main theoretical result. I want to spend a few minutes talking about the empirical analysis. So in the empirical analysis, what we're going to do is try and construct the exact empirical analogs to those theoretical comparative statics that I just showed you. What happens in an empirical model as we vary the amount of complexity? How does the performance of prediction and how does the performance of trading strategy performance, how do these vary with complexity? So to do this, we wanted to do this in the most obvious setting you can think of. Think of it as a total cornerstone aspect of empirical finance. We're going to forecast market returns, right? So the CRSP valuated index or S&P 500. We're going to forecast market returns at the monthly frequency. And the nice thing about this is that we have a fairly well agreed upon set of predictors because this is such a highly developed literature. So the predictors that we're going to use, the G's in that original slide that I was showing you, that vector of G predictors, we're going to use 15 predictors from the Goyal-Welch survey of 2008. All right. Now, the trick here is that if I have 15 predictors, I need to investigate my theory by ranging models from simple to highly complex, right? So I need to be able to hold that set of predictors fixed, but vary the number of parameters in a model. How do I do that? Well, we're going to use a neural network to do this. The basic idea is that we're going to produce from our original set of 15 predictors some basis functions. If I want to have a very simple model, I'll just build one basis function. The way we're going to build our basis functions is to use a form of neural network called random Fourier features. It's a neural network in which you simulate these initial weights. You just randomize them as opposed to estimating them. But this is just another form of a neural network, right? So if I want to produce one predictor, a very simple model, I'll draw one set of weights, a 15-dimensional vector. I'll use that vector to add up my 15 signals G, and then I'll take a nonlinear transformation of them, right? That's my activation, and I end up with one predictor. If I want 1,000 predictors, I'll draw 1,000 weights. I'll build 1,000 such functions. They'll all use the same activation, but they'll all combine the predictors in a different way. If I need 10,000 predictors, I'll do this 10,000 times. So you can see how with a structure like this, I can hold the set of input information fixed, but vary the size of the model in which I use that input function. All right, so I'm going to show you results that vary model size from C equals 0 to C equals 1,000. We're going to look at very complex models. All right. One point about this empirical analysis, I need to show you out of sample results, of course, to correspond to the theory. And the way that we're going to do this is we're going to do very standard out of sample analysis from asset pricing. We're going to have a rolling window. In each window, we're going to estimate a model. then we'll forecast one period out of sample, roll ahead, redo the estimation in sample, forecast one period out of sample, do this over and over, and I'll show you the average performance in the out of sample periods. In the results that I'll present here, I want to use a small number t. I'm actually only going to use 1 year of monthly training data for my analysis. In the paper, we do a whole range of analysis, different training windows. I'm going to show you the t equals 12 results here for 2 reasons. One is that when t is smaller, I can get to a high complexity faster, right? If t is 12 and I use a p of 12,000, I can get to a complexity of 1,000 with less computation than if I used, say, t equals 100. That's one reason. That's actually a small reason. It's not too hard to compute. The bigger reason is that I want to be able to demonstrate that this virtue of complexity shows up in surprisingly small samples, right? So let's take a look at what these results look like. So what I'm showing you here is a set of plots that are designed to have the same structure as the theory plots. On the x-axis, I have complexity. And then in panel A, I have expected returns of the trading strategy, volatility of the trading strategy, and Sharpe ratio of the trading strategy. So the main point here, if you summarize these results in one slide, the out-of-sample behavior of complex models exactly aligns with what we see in the theory. As I increase complexity, the approximation power benefits show up as an increasing expected return. This is true for something like a ridgeless model. Here we approximate ridgeless with 10 to the minus 3 as the ridge shrinkage, and we look across a range of shrinkages. That's what each of these lines are. Regardless of shrinkage, as we increase complexity, expected returns of the trading strategy out of sample are increasing. Volatility behaves also exactly as the theory suggests. It's increasing until we hit C equals 1. Once we move past C equals 1, the volatility of the trading strategy retracts, comes back down, and is continually decreasing, eventually flattens out. This implies then, of course, that the Sharpe ratio pattern is exactly like what we see in the data, right? As I increase complexity, this spike in volatility means that the Sharpe ratio takes a dip at C equals 1, but above C equals 1, the Sharpe ratio is strictly increasing. One thing that I'd like to emphasize, by the way, is that I'm going to flip back very briefly to make this point. I forgot to make it a moment ago. One thing that you see here is that the Sharpe ratio here for a trading strategy is never negative. This comes from the fact that the numerator of the Sharpe ratio, the expected return in a prediction model, is always positive, right? You can't get an expected negative out of sample performance from a prediction model. The worst you can do is get 0. If you work through the math on that, you'll see very quickly, it's just a statement about expected returns are quadratic objects, because the signal that you're trying to capture once you build your beta is going to have the signals themselves in it. You'll get a signal times a signal. It's a quadratic object, and that's why expected returns from a predictive strategy should always be positive or 0, right? So that means your Sharpe ratio can't go negative, because of course you also have a quadratic object in the denominator. The worst case scenario is that the Sharpe ratio is 0, right? And that can happen even in complex models if you're feeding it useless information. I want to contrast that with what happens with R-squareds. Notice that R-squareds in prediction models can be arbitrarily negative. Even if you have a good model, you can get very large negative R-squareds. The reason being is because R-squareds are very sensitive to forecast volatility. So if the true model is y equals x, and I build a predictor y equals 2x, I have a predictor that's perfectly correlated with the true model. It will be an optimal trading strategy if I trade on that, because that 2 is going to cancel out of the numerator and the denominator of the Sharpe ratio. But for R-squared, it's going to look like a terrible model. So an important point to make here is that in these empirical results, we see substantial positive Sharpe ratios. But if you think about contrasting this with the Goyal-Welch analysis, Goyal-Welch say you can't predict out a sample when you're doing market return prediction. The R-squareds are always negative. That's fine. R-squareds being negative does not tell you about the quality of a model from a finance standpoint. If you want to evaluate whether or not you have a good prediction model, you need to be looking at Sharpe ratios, right? So I'm not going to spend a lot more time comparing to the Goyal-Welch analysis. We have a lot of results in the paper along those lines. I'm going to briefly show you what the predictions look like from this model. So what I'm showing you here are the estimated expected returns. Let's just, for the sake of time, focus on the blue curve. The blue curve are the expected returns on the market from the most complex model that we've analyzed, C equals 1,000. And what you see here is that the patterns are very interesting in the way that this strategy builds its expected return. First of all, it's essentially a long-only strategy. It takes a long position in expansions and zeroes out that position going into contractions, right? This has an interesting connection with the prior literature on return prediction. For example, John Campbell has some work that says that if you impose a simple economic restriction like expected returns should never be negative for the market, simple equilibrium restriction from finance, you can improve the forecasts and trading strategy behavior in a timing strategy. We get this without telling our model to do it. The machine learning model learns to be a long-only strategy, to never use negative expected returns. The other thing is, when does it take these zero positions? When does the timing strategy trade out of the market? It does this going into recessions. So there are 15 recessions in the sample. In 14 out of those 15 recessions, the trading strategy basically zeroed out its position in the market. The only one that it missed was this short recession after World War II. All right. Now, I alluded to some follow-on work here. In the empirical analysis, I showed you a result where they show up in any asset class you would consider. So we do time series prediction of different types of US equities. We look at international equity indices. We look at government bonds, look at commodities, every kind of commodity, agricultural commodities, energies, metals, and so forth, currencies in developed and emerging markets, interest rates. In all places, we find the same pattern. If you're forecasting returns in these asset classes, you're going to improve the performance of a trading strategy based on those forecasts using a larger model. Now, all of these results in this paper and in the Everywhere paper are about time series prediction problems. In problem is different in two ways. One is that instead of having one asset, I have a very large number of assets, an arbitrary number of assets, if you will, N. And two, it really boils down in a factor pricing model to finding an SDF, right? The SDF is about finding the maximum Sharpe ratio combination of those N assets. So in this problem, we do two things. We look at the panel setting and we look at a different objective function. Instead of training a model to optimize mean squared error like we do in regression, we're training a model to directly optimize portfolio Sharpe ratio, right? That is the SDF estimation problem. So it's a different theoretical can of worms, but what you find is a same qualitative result, which is the best factor pricing model you can build actually has the largest number of factors that you can put into your model. Factor model performance on an out-of-sample basis. The factor model that increases the number of factors will lead to a reduction in the pricing errors from that model on an out-of-sample basis. And then we have some other extensions as well, but in the interest of time, I'm gonna jump ahead to the conclusion. Okay, so the first conclusion I want to make here. So asset pricing as a whole, not to mention the investment industry, both of these are very much in the midst of a boom in machine learning research. This problem was prompted by that boom, and a lot of the skepticism and interest and uncertainty and also some of the, what I would say are misleading statements that get made about machine learning. We wanted to have a deeply anchored, theoretically anchored statement about what we should expect from machine learning when we apply them in finance settings. And that's the idea of what we tried to deliver here. And we end up with a result that we think is surprising and interesting, contrary to conventional wisdom. Larger models generically improve model performance, okay? All right, one point I want to make here is that this is not a license to put arbitrary predictors in your model. It doesn't say that you should go out searching further and further for new predictors to introduce. What it means is that you should use all of the plausibly relevant predictors that you have at your disposal, but use them in rich nonlinear ways rather than in simple linear specifications. If you have sensible input predictors and you allow yourself to use them very flexibly, you'll give yourself prediction benefits, portfolio benefits, and you can enjoy these benefits even when the training data is scarce, and especially when accompanied by further shrinkage. All right, we show that this is true in a number of empirical analyses. The last conclusion I want to leave you with, right, comes back to how I started this talk. So machine learning clashes with this philosophy of parsimony. In addition to Tukey, George Box himself was very vocal about this point. He's famous for a couple of things. So for example, most people have heard his quote, "All models are wrong, but some are useful." This is another quote that I think is particularly relevant for this discussion here. "Since all models are wrong, the scientist can't obtain a correct one by excessive elaboration. On the contrary, like Occam's razor, he should seek an economical description of natural phenomena," i.e. he should use small models, right? "As the ability to devise a simple model is the signature of a great scientist, the tendency to build too big of a model is a sign of mediocrity." And I find this a very interesting juxtaposition because all models are wrong. We cannot specify the correct model, but we know that only if we have the correct model should we be using a small version. If we don't know the functional form for a model, we have to use an approximating model. And our results here show you that you will do better. It's a mathematical proof. You will do better if you use a larger model. So I find this juxtaposition interesting. And we may wonder if this means that there is some blunder to the Occam philosophy, right? In some settings, it can be true that Occam's razor is a good way to distinguish between models. But here is a very clear example of a setting in which it doesn't hold. A small model is only preferable if you're correctly specified. If you're not correctly specified, if you have to do any model approximation, then a bigger model is better. All right, so I'm going to stop there. I think we've set aside a little bit of time for questions, but thank you all in advance of the questions for taking the time to show up and listen.
Thank you very much, Bryan, for this very insightful talk. So we open the floor for some questions and answers. If you have any questions, any comments for this? Yes, Junya, yeah. I'm not sure, yeah. You probably need to come to the podium so that Bryan can hear you. Yeah, sorry, Bryan, we were having some technical issues.
Kind of, yeah, complicated. Yeah. So I just ask a question related to your Sharpe ratio plots. So we see from both theoretical part and the empirical part, your Sharpe ratio increase significantly with respect to constant C, right here. So I'm wondering whether you have a, because I mean, Sharpe ratio cannot be increasing forever, right? I'm wondering whether you, in your theoretical part, do you have any results on the theoretical result on the upper bound of the Sharpe ratio in your case? So this is my question.
Yeah, it's a great question. So yeah, you see in the data here, after you get to a complexity about 50 or 60, it more or less flattens out. What determines the point at which it flattens out? It depends on two objects. It depends on the true total degree of predictability in your model, in the data generating process. So you can think about that as what is the true magnitude of the betas, right? The second is what is the eigenvalue distribution of the covariance matrix of the signals, right? So if we flip back here, right, it's really these objects that are critical to understanding the behavior of models and on the high complexity setting. What is the limiting behavior of this covariance matrix? Depending on its eigenvalue distribution, you will require higher or lower levels of complexity to reach that sort of flattening out point. And then what is the total amount of predictability? What is the magnitude of the true beta, if you will? Those two things together determine the shape of those virtue of complexity curves. Yeah, I should emphasize that in the paper, right, we have the full complete expression of this theory, right? What I focused on here is just showing you one particular calibration that I think is good at conveying the intuition and a visual understanding of what the theory is saying. But the details of the theory are all in the paper.
All right, so we have several more questions. Ladies first, and then followed by Xiao. Please come forward and speak close to the computer.
Okay,
speaker.
Thanks for the very excellent talk, and I enjoyed it a lot. Thanks for the lady first. So actually, I do have a question regarding the Sharpe ratio. So similar the picture. So the problem I have in mind is I wonder how precisely those Sharpe ratios are estimated. So now only the value itself is kind of reported, but kind of say the standard deviation of the Sharpe ratio, could that some say interval estimators, maybe the performance is kind of similar? I'm not sure. That is the question in my mind. What about the statistics of the Sharpe ratio? Thank you.
Yeah, that's a great question. So so we can characterize something of the distribution of the Sharpe ratio here. What this is reporting is the expected out of sample Sharpe ratio. The distributional theory is more complicated, right? Getting to the expected Sharpe ratio is very complicated. Being able to do any sort of inference on the distribution of Sharpe ratios in the data is not something that we've tackled. I think it's doable, but it's going to be quite involved. Theoretically, we could describe a little bit of the behavior of the Sharpe ratio in terms of its distribution, but you're right, that's not a component of this paper. Everything here is about the expected out of sample Sharpe ratio. So it's a fair point. There's a distribution around these. This is the mean of that distribution.
So,
Hey, Brian, this is Xiao.
Good to
So
see
I
you.
think, all right. So I think, we were talking about the bias variance trade-off this morning a little bit related to a couple of different sessions. And I guess we typically have this, this intuition that if we have a parsimonious model, then the bias is high, but the variance is low. Whereas if we have a more complex model, the reverse is true. Can I interpret your results as the following? Because all models are approximations, once we take into account model uncertainty, then the smaller models not only have high bias, but also high variance because the model misspecification risk. So that what you're doing here is you're reducing the bias, of course, with a more complex model, and you're able to control the variance as well with regularization.
Yeah, that's exactly right. I couldn't have said it better, right? So the way I think about this is that small models have a very strict form of bias, right? Large models have a much more thoughtful form of bias. Okay, so what I mean by that is when I write down a parsimonious model, right? When I do what economists typically do, which is like take this audacious step of saying that I know the model specification, I'm actually imposing an extremely strong bias, right? I'm specifying the model, right? I'm saying that essentially anything that's a functional form outside of what I've specified has a zero coefficient attached to it. It's a dogmatic bias, right? So that bias is large, it's strong. When I go to a complex model, I introduce bias because I start to introduce this shrinkage, right? Complexity requires shrinkage to go along with it. But what I'm doing is I'm doing it in a way that allows myself to first consider all kinds of functional forms and then shrink after that. So I almost think of it as when I do model specification, I shrink before I see the data, and before I see the training data, right? And when I do machine learning, I shrink after I see the training data. So you're actually shrinking with more information in the latter case. So it doesn't mean that you can't impose things like other economic priors and so forth. You can do that in both settings, right? But if you impose an economic prior that's strict so that you don't allow yourself to estimate flexibly any part of your model, then your bias is just all else equal stronger, and that leads to the worst performance of small models.
Thank you. Please, yes. We have quite a few more. I hope you have some time to spare.
Sure.
So I have a question. Dr. Cheng talked yesterday about adjusting the APT trading model for the fact that you have to estimate it. And I worry that, you know, as you go put in these larger and larger settings, that what does that do to that kind of effect? I mean, does having a Sharpe ratio necessarily mean that it's going to be better for somebody to make a decision on? Or is it, in fact, you're increasing, you know, noise to the extent that you could lose some of that? So anyway, so there's a trade-off, it looks like, in his results about the, you know, potential complexity of the model and the variance that could create with the ability to actually use it. You know,
Yeah.
in his model, if you take account of the estimation error, it's not so clear you can use models that look like they fit better. So
yeah, so it's an interesting question. It's interesting to juxtapose these two. So the right way to think about this is a comparison between perhaps between Dr. Cheng's paper and the factor pricing version of the virtue of complexity. So not this paper that I presented, but one of the follow-on papers. And one thing that you see is that some of the assumptions that I don't think there are all the assumptions that Dr. Cheng uses, but the core set of assumptions that he uses essentially constrain the extent of complexity necessary to do estimation there. So there's something to keep in mind in that regard. But I think that the important point is that there is uncertainty in any of these approaches that you would take, whether you take a small modeling approach or you take a large modeling approach, right? But you're actually putting yourself in a position to introduce less noise into the model by being open-minded in the specification, right? So you'll introduce more nonlinear functions. Not all of those nonlinear functions are going to be useful, but you're going to be shrinking all of the nonlinear functions that you introduce, right? In a way that sort of is designed to optimally mitigate the noise that goes along with it. When you use a small model, right, you have no way to control that. You have no way to sort of modulate the amount of shrinkage. The shrinkage is dogmatic, and therefore the noise that arises from that dogmatic shrinkage is unavoidable. In any case, it's a good question. It's a complicated question. The details of how you make that comparison are a bit tricky to do in a Q&A.
Thank you. Thank you for this very interesting and insightful paper. I see your theoretical part relying on the random metric theory. I don't know the details, but I guess probably some IID needs or uncorrelated needs is needed as an assumption for the random metric theory to be applied here. I'm not sure. And in your applications, the predictors, those Welch-Goyle predictors, those time series, they might be persistent. So I'm wondering how sensitive or how robust is your method to the potential persistency in the data in the predictors?
Right. Yeah, that's an interesting question. So Yeah, the time series properties of the predictors are not something that we spend a lot of work trying to be general about in the setting. What we spend most of our time being general on is the cross-sectional correlation structure, which is the thing that shows up in that SS prime matrix that is at the core of our random matrix theory. Introducing time series dependence, makes that covariance somewhat more complicated, because now you need to be thinking about dependence in 2 dimensions. We've actually toyed around with that a little bit. I don't think it actually has much of an impact on the qualitative descriptions. Think of it as it's going to have impacts on the shape of these curves, right? In terms of like the level, the point at which they start to flatten out and so forth. But I don't think it has any qualitative impact on the virtue of complexity itself, the fact that these curves are increasing. This is a good question, though.
Okay, great. I will ask a couple of questions to finish off our keynote speech. So, Bryan, your result about complexity is virtual, at least in terms of return forecasting, maximizing Sharpe ratio is very striking. So I wonder if you enforce some kind of economical restriction, say in the time series, the predicted return, if you want them to be positive, would this interfere with your funding about complexity, bigger model is better?
Yeah, so very generally, the way I think about this is there's nothing about the theory that precludes including priors, right? In our derivations, we do it in a basic setting. We don't have any economic priors here, but the way you should think about complexity is if you have model views, right? If you have priors, if you know something about specification, you should impose those. But then you can think about the orthogonal aspects of the model. After you take into account your priors or your specification, there will be some parts of your model that you don't have a view on. And that's the virtue of complexity is going to apply directly there, right? So if you want to actually fold these together, you can, right? It's going to require a more sophisticated setup, but the conceptual point doesn't change. In the parts of your model in which you don't have a prior, right? Virtue of complexity is going to apply. You're going to benefit from flexible approximating approaches.
Also, thanks. At one point, you gave a caveat. You said your result is not a license for people to go look for more predictors. You say is within the given reasonable predictors using more parametrization helps. I kind of wonder why that's the case. Why such a caveat, especially say in the cross-section.
Yeah.
Even though there are strong factor, there are weak factor, maybe some factor become not so strong in a particular sample period, but they might be useful in the future. Why you are, given this caution about kind of going for, the 500th or 1000th predictor if
Right.
your model is better.
Think about it this way. So this is a good question. Think about it this way. The way I get a result like this is to say that as I add complexity, I'm adding new predictors. In a neural network, it's because I'm adding new nonlinear functions of the fixed set of predictors, right? That means that when I add new functions, I'm adding them in a sort of exchangeable way. When I build a neural network, I don't prefer one node to another. But when I go out and I gather data, I do prefer some of these predictors to others. I'm going to introduce the most plausible predictor first, and the next most plausible second. And by the time I get to the 1000th predictor, it's going to be a predictor that I sort of ranked the 1000th most important. That means that as I increase complexity by adding more and more predictors that are each of them weaker and weaker, you aren't going to get an increasing curve like this, right? So another way to think of it is if I add all else equal, an additional predictor to my model that is pure noise, I'm not going to get the virtue of complexity. There is no virtue to adding noise to a model, right? Where there is virtue is to adding better approximating uses of a given set of predictors. So hold the set of predictors fixed, use them in more flexible ways. You're not going to do worse by using them in more flexible ways. As long as the predictors are useful at all, you'll do better by using in more flexible ways.
Right.
Does that make sense?
Right. The key is to know whether the additional predictor or factor is at least weakly useful or not, right? You don't want to add a pure noise.
Yes.
And just right. So I guess your point about complexity or bigger model better is more about for the fixed set of parameter generate more basis function because that can approximate the truth better and better, right?
That's right.
Yeah.
It's very
But
much
you
a neural network perspective.
Yeah, you kind of don't take a stand on what are the, whether it's 18 time series predictor or 200 cross-sectional predictor. It's more about fix a set of predictor that the literature have proposed and try to use richer parameterization and actually turn, different from the standard parsimony model. You actually show if they offer that, when we include more and more parameter, it can actually be better. Okay,
Yeah.
great. Thank you.
I would also add to that one additional point, which is if I have, 10 predictors that I feel strongly about, yes, I should use them nonlinearly. But if I also have 200 predictors, the point is that a large parameterized model using those 200 will also be better than a small parameterized model using those 200. The way you should view these results is whatever input set you decide on, hold that input set fixed. Then as you vary complexity around that input set, how nonlinearly you use it, you expect to do better using a more flexible representation.
Right. It almost sounds like, once you understand, it almost sounds like higher order Taylor series expansion give you a better approximation than just a linear or quadratic approximation.
Well, that's exactly right. Taylor expansion is just one approximating method, right? It tends to not be a very good one from a statistical standpoint. And I think because it's in some sense very different than a neural network, right? A neural network is one approximating model. A Taylor series is another approximating model. But the Taylor series introduces its approximation in a less democratic way, if you will, right? It's the first term that's most important, the second term that's next most important, and so forth. In a neural network, it's the fact that all of these terms are being simultaneously generated, and from an ex-ante perspective, they're all equally likely to be important. And I don't really know what it is about that structure. I don't know if it, maybe somebody in the ML community knows the answer to this question, but for some reason, that structure tends to work well. The fact that you don't prefer certain nodes over others when you build the network.
I see.
And I think it's a very interesting feature of the empirical phenomena we've seen around neural nets.
Bryan, thank you for so many insights to share with us today. I know it's perhaps quite late for you. Thanks again for being here.
Thanks for having me. It's been an honor.
Some people want to ask questions, but we need to move on. We have 2 other papers later in the section. But wherever you are, I think I heard you are in Europe. Take good care. See you.
Thank you. Bye-bye.
Yeah, bye-bye.